Okay, so and these are our final units over area and volume. We already kind of know how to do area. We know it's just the depth integral between left bound and right bound, but we're going to explore formula for different scenarios, and we'll spend our time working on area today and tomorrow. And after that, we're going to shift over to volume, and there's three different scenarios or unique scenarios for volume. We'll spend 3 days over that. But I think we'll have a lot of time for review. I'm not gonna force the quiz. Actually, I say test here, but it's just going to be a quiz. I'm not going to force this quiz next week. I feel like we can kind of take our time a little bit. So we'll have some time next week to do review, get really comfortable with everything. Next Friday, I do want to have a test next Friday, so I want to kind of start our AP review a little bit and kind of go over a very specific type of FRQ problem next Friday, and then there's a 3 days of no school that second week of March. So I'm going to have us have another test review day or quiz review day, and then the quiz on. Okay. I think it's the last unit. Like that's our last one. Yeah, that's this. I may adjust some of the schedule after that in terms of AP, how we're going to organize our AP review. But the idea is that during AP review, we're still going to have quizzes and tests, but all your quizzes and tests are going to be balanced out with your homework grades. So your homework grades are going to go in with your test grades or quiz grades. So it will count like 50% homework, 50% test. So hopefully that will be a good motivation to do your homework on time so you can earn the majority of the points. Consider basic preview points as long as we're doing it, as long as we're keeping up with our work. Okay. So we're going to send over a month review. Yeah. So our AP exam is not until May 13th. So I mean, we're ending our we're having a final test over these topics on March 15th. So that's basically too much. And you guys will review that too. Oh yeah, there's gonna be a lot of I mean, this is gonna feel like a full unit or multiple units. Because we're gonna do a review from first semester, and so yeah, there's it sounds like a lot of time, but we do need all that time to remember all the things that we've done so far. Yeah. I'll go over all that in detail. It's about 3 hours. It's like a few seconds, right? Yeah, FRQ, and I'm assuming that all AP exams are kind of along that. Yeah. Okay, yeah. So most of you guys have experience with AP exams, kind of have that. But yeah, I'll go over all that detail when we get closer. What's the best one about that? Yeah. After like your last day of senior year, like if you did like Cool. Are you involved in what we did like the last two? Like there's different stuff. Oh, you mean this one here? Yeah. Yeah, I think you're gonna recognize a lot of this area from our integrals unit this semester. So All right, let me start off by going through the easier of the two options. This is a vertical orientation. This is where, let's say you want to find um, the area of this region here between the graph of f and g. And really, we just have to identify the top graph, and then we subtract the bottom graph. The top graph is the one that is visually higher up on the y-axis, and the bottom graph is the graph that is lower on the y-axis. And then we identify our left bound and right bound. We put it into our integral formula, and then whatever answer we get, we're now going to be guaranteed that whatever number we get, whatever answer we get, is going to be positive. Remember how before we're doing depth intervals, sometimes we get a negative number. Now, if we do this top minus bottom formula, we're always going to get a positive number. And now we can call this definitively an area, because we're never going to get a negative answer if we go through this process. So in this case, which is the top graph that you see, F or the G? Yeah, F is the one that's higher up. Now, obviously, after they intersect, this is going to be flipped, but we're only talking about this region here. So the F graph is the top function, and the bottom graph is the G function. So if you want to find the area of this enclosed region here, we just do the depth integral from a to b, whatever those x values are. And then the top graph, f of x, minus the bottom graph, g of x, and dx. Okay, so the idea here is that I'm going to do a representative rectangle. The idea is that we're adding these infinitely thin rectangles from one end all the way to the other. And the f of x minus g of x is adapting to each of the heights of each of these individually thin, infinitely thin rectangles. So here, this rectangle will be f minus g. This rectangle here will be f minus g. Obviously, we're making the formula doing all the work for us, but the idea is still there, is that this f of x minus g of x represents the height, and the dx represents these infinitely thin width of our rectangles. And hopefully we see that we still have this rectangular area formula built into this interval here. Yeah.
We put for like a bunch of equations in the form of y equals
Oh, you mean here, like this?
up in the box. Top of the,
Oh, over here?
yeah, so like the bottom of it, the equation in the form of y.
Oh, right. The forms, equation in the form of y equals, that just means that the equations that we're going to be working with all are going to look like this. They're all going to look like y equals, could be like y equals x squared, could be y equals. Yeah. But the reason we want to talk about this form is because on the next page, some equations are going to be a different form. It could be like x equals y squared, x equals y cubed minus 3. Then we're going to have to do a different formula. But these are basically going to be functions that we're going to recognize like this, right? We recognize y equals x squared, y equals 2x plus 3. This is going to be this nice vertical orientation for our area. Okay, so this second example here, we want to find the area of this shaded region. And what's the top graph that you see? F of x, right? So the top graph is f of x. What's the bottom graph? I know where you're looking, but what's the equation of this line? Y equals 0. It's the x-axis. That axis tells us the x-axis. But the equation of this line is y equals 0, right? So if I want to do top minus bottom, depth integral from where are my left and right bounds? Where to where? From A to B. And then we just go through our formula, right? Top graph minus bottom graph. Our top graph is f of x minus, so just minus what? Minus 0. And then the 0 can just drop out, right? So really, it's just a depth integral from a to b of f of x. Now we recognize this, right? We've been working with this formula before, and the reason I want to kind of show you this whole process is that we have been using the x-axis this whole time. We just haven't identified it because the assumption is that it's always going to be with the x-axis. So that minus 0 is ensuring that we do have a bottom function, and our bottom function has always been 0. Up to this point. But because our bottom function is always 0, sometimes if this is the one that's on top, then that's why we're getting a negative number before, because we didn't have the top minus bottom. We just always did integral of the function. So for instance, let me do example 2b here. Let's say I have this graph here. If I want to find the area of this region, I would also want to do top minus bottom. And in this case, what's the top graph going to be now? 0. So it's going to be 0 minus what? Minus g of x, which is just negative g of x. And this will make sure that we get a positive number in return, because if we just did g of x, then g of x is going to accumulate all of these negative y values. And that's why before with definite integrals, we would sometimes get positive numbers, sometimes we'll get a negative number. And before it was, if we have more accumulation of values below the x-axis, that will always give us negative. But now if we always do top minus bottom, then we're always going to ensure that we're never going to get a negative number in return. Okay, so let's look at some specific examples. And then we can also use our calculator to do some of this work for us. But initially, I think we're going to just do it by hand, and then we can use the calculator. So it says, find the area of the region bounded by y equals x squared. So that's the parabola here. And y equals 2x plus 3, that's the linear graph here. So we want to find the area of that region. What's the top graph you can see here? Yep, that's the higher one. And then the one that's below is the square. So we know what the top minus bottom is going to look like, but our steps say we're going to find the bounds first. We're going to find the points of intersection, because the points of intersection are also going to act as the furthest left and the furthest right of our shaded region. So the way we find points of intersection, we set the equations equal to each other, and we just solve for x. When we solve for x, we can find points where they intersect. Okay. So intersection. All right, so if I want to solve this quadratic here, how would you go about doing that? Bring everything over, set equal to what? 0, right? Okay, so do our factoring, multiply to be -3, add to be -2. Yeah, we know it's going to be 3 and 1, just have to figure out the signs there. So -3 and +1, just double check. X squared minus 2x minus 3, okay. And then we solve for x equals 3, and x equals -1. Okay. We see it in our graph here as well, right? -1. All right, so now let's go through our area formula. depth integral from where to where? -1 to 3. Okay. Top graph minus bottom graph. So what do we put down first? 2x plus 3, and then minus x squared. Now, this is what I think is this is a really good habit. If we can build this here, is that whenever we have anything following the minus sign, always put it in a set of parentheses. It may not matter for this problem, but why do you think this is a good habit to build? No. Right, so it applies to everything that comes after. Now, obviously, there's only one term here, so without that parentheses, it won't matter. But if there were multiple terms here, we want to make sure we subtract everything that comes after it. So I'm going to keep reminding us, whatever you write down on paper, put your bottom function in a set of parentheses, and that way you'll remember if there are multiple terms, the negative is going to distribute through.
Which one, where you put the 3 or negative?
It does, yeah. We want to go from left to right. Want to start your bottom, your smaller value, your furthest left to the furthest right. Smaller to larger. Okay, I think we work this out by hand, right? Because this is just a depth integral problem. We're going to just solve this by hand. For every term, we can use what? Power rule. So 2x squared over 2 plus 3 becomes minus over 3, okay? And then we can work the bounds in, so half bracket, -1, and what number gets used first? Upper bound, right? So we have 3 squared plus 3 times 3 minus 3 cubed over 3, and then what comes after this? Subtract, big parentheses, and we do the same thing for the lower bound. Okay. All that gives us 32 over. Yeah, you want to put a big parentheses here after the minus one. Yes, we are going to do calculators, but right now, yeah, you'll get to use your calculators on your quiz. But right now, I want to just have us do things by hand. Okay, so I think this feels pretty familiar, right? In terms of the setup, we're used to working in terms of x, in terms of our functions. But the next page, we're now going to have equations or curves that are not necessarily functions, but we can still adapt the area formula for non-functions. So non-functions are ones that don't pass the vertical line test and have equations that look a little strange in terms of, x equals y squared minus 3, or equations where the x's and y's feel like they're flip flop. So let's look at the next page. So this is what we call horizontal orientation. These are imagining that we're stacking horizontal rectangles between graphs, and our equations, our formula will look a little bit different, because now instead of reading the graph from left to right, we're going to read the graph from bottom to top in terms of our lower and upper bound. before our left and right bound were our boundaries, but now our y values are our boundaries. So imagine we're stacking all these rectangles horizontally from the bottom to the top instead of vertically from left to right. We can tell that these curves are obviously not functions, right? These graphs, neither of these would pass the vertical line test. But we're dealing with these equations that are not functions, but we can still find the area of these non-functions as long as we identify where these graphs are located. So we have a graph on the right minus the graph on the left between y1 and y2. And our equations will look a little different because our equations are going to be in the form of x equals y squared or x equals y squared minus 3y plus 4. It just feels a little bit strange with the equations, but these are going to be equations that we're going to, we're not necessarily have to graph them. We just have to be able to know how to adjust our equations so that we can put it into our calculator. So we have x equals f of y. Okay? And then we have x equals, it's kind of hard to see, x equals g of y. So we want to use this formula here for these curves that are obviously not functions. We can set up our area formula this way. We can go definite integral from lower bound to upper bound. What's the lowest y value that you see and the highest y value that you see? C and D. Okay. Okay. All right. What's the graph on the right? F of y. Then what do we do? Minus g of y. Then dy. So if you can imagine, all these infinitely thin rectangles are going to be stacked horizontally. So all these really thin rectangles are just stacked from the bottom to the top. And that's how this is accumulating and finding area for us. Very different, or a little bit different than we saw on the previous page, right? Previous page, we're stacking rectangles vertically from left to right. Now we're stacking rectangles horizontally from the bottom to the top. Okay, so example 4 is one where we can work this out by hand because our equations are in the proper form. Okay, so we want to find the bounds. So we have these equations, x equals y plus 1. So you see how these equations look a little different here? X equals 1/2 y squared minus 3. These are not in the form that we're used to. But if you see an equation that's x equals, then whatever's to the right of it is going to be a good fit for our right minus left formula. Just like how if we see an equation in the form of y equals x squared, y equals 2x plus 3, these are going to be the good fit for a top minus bottom formula. So these are the ones that we recognize more. The x equals are going to be the ones that we're less familiar with. Right, so let's go ahead and find our intersection between the two graphs. We can find our lower and upper bound. So how can we do that? Yep, so we can set 1/2 y squared minus 3 equal to y plus 1. And this is the quadratic that I want to be able to factor. So if I multiply everything through by 2, it makes it a little bit easier to factor without having to deal with that fraction. So if I multiply everything through by 2, I get y squared minus 6 is equal to 2y plus 2. Let me bring everything over to one side so I can factor. Okay, multiplies to be -8, adds it to be -2. Y minus 4 and y plus 2. So y equals 4 and y equals -2. So that's consistent with what we see here. Our lowest y value is -2. Our highest y value is a +4. Okay, so let's set up our area formula. Depth integral from we're not doing top minus bottom anymore. We're doing right minus left. So the graph on the right is what? This one. And the graph on the left is, yeah, the 1/2 y squared minus 3. We do want to put it in a set of what? Parentheses. Now, I like to just have a representative rectangle. I think this will be really helpful when we talk about volume down the road, but we just want to show, you know, you can put the rectangle anywhere, but this is just a representative rectangle of how the rectangle is stacked. They're stacked horizontally from down here all the way to up here. And you can see that the right endpoint of my rectangle is touching the right curve, and the left endpoint of my rectangle is touching the left curve. So just as a reminder, right endpoint is talking about this graph, left endpoint is talking about this graph. Okay, so we can try working this out by hand here. We can go through power rule, or let's clean this up here. Right, so we do power rule for each of these terms here. All that gets us 18. All right, example 5. Represent the area of the shaded region to the right using the integral notation. So, how many depth integrals do we need if we want to find the area of these two regions? We need 2. Why is that?
Yeah, openings.
Okay. Also, is the top function going to be the same here as it is over here? They're going to what? They're going to change, right? Because they're going to intersect in a way where the top function here is going to all of a sudden be the bottom function here. So if we just do one depth integral, then we're going to probably get a negative number because this is going to end up subtracting the opposite order that we're that we're hoping, then, different than what we're hoping for. So let's just set up our two definite integrals here. What's gonna be the boundary of our first region? 1 to 2, right? That's the furthest left to the furthest right of our first shaded region. The top minus bottom here. If these are functions, f of x and g of x indicates that these are functions. What's the top graph of my first region? Yeah, f is the curved region, right? Minus g of x. G of x is my linear graph. Plus definite integral from put the graph on top. Then minus, yeah, now it's the curve. The curve is now on the bottom. We can't solve this because we don't have, it's just asking us to represent using f and g.
She's the one that remains straight right now.
I'm sorry?
She's the line that remains straight.
Yeah, g is the linear one, and f is the curve.
What would be a function we would solve?
I would have to give you more information. I'll have to tell you what g and f are. Okay. Okay, if you have your calculators, we're just going to practice seeing if we can get these to show up in our calculator and be able to graph them. And if it's harder to graph the non-functions, but we can still use our calculator to find our boundaries. Back to example 3 on page 1. So if I have my function y equals x squared, my function being 2x plus 3, I like to do zoom 6. Zoom 6 just gets me to a standard window.
What do you do to get to that graph?
If you do zoom, standard, zoom 6. Oh, sorry. Oh, what do you type in? So I typed in y equals x squared and 2x plus 3. So just the two equations that are in example. Yeah, just hit graph. Yeah. You get it?
Yeah, yeah.
If you feel like this is a little bit, right at the edge, if you want to push that y-axis up a little further, you can always go to your window and adjust your window max, right? Because right now, your window y value is showing up to 10, but if you want to see a little bit more than that, you can push it up to 20, for instance, and that should give you a little bit more room. You see that intersection there? If I want to find let's say I want to find that left intersection between the two graphs, I can do second trace intersect. Second trace intersect. Once you get there, then it says first curve. So if you toggle between your up arrow, down arrow, it'll jump between the two curves here. So what you can do is you can move to a point that is close to your first intersection, hit enter, and then it'll go to the second curve and hit enter again. And if you hit enter a third time, the calculator will look and find an intersection. If you just find points that are close to your intersection, the calculator will look for the closest intersection. So this one ends up giving me intersection -1, 1. -1 is the x value of my intersection there. And if I want to find this second intersection here, I can do second trace, intersect. And now you're just going to scroll to a point near the intersection that you're targeting. Don't put it directly on the intersection because then the calculator will get confused and won't know which graph you're talking about. It says first curve, question mark, hit enter. And then that blinking cursor should now be on the other graph. Hit enter again. And then now the calculator just knows that it's looking for those two intersections, those two graphs. Hit enter again, and it'll find that intersection for you. Yeah, when it says guess, you hit enter, and then intersection is 3, and that's what we found here.
Is there eventually gonna be like a time where you're like, that's the calculator, like whole numbers?
Right. So tomorrow we're going to really explore problems that are meant for calculator with really just the setup that you have to do, and then the rest is calculator work. Okay, so now let's see if we can do the depth integral that we have here. We can enter all this into the line if you want to under Math 9, and just do 2x plus 3 minus x squared. I want to show you a different way, especially when we're dealing with volume and you don't want to have to enter everything into the same line. It just feels messy with all the parentheses involved. So I'm going to have us practice this. We're going to let y1 and y2 hold your two functions, which they are already for the most part. I think most of us have x squared y1 and 2x plus 3 being y2. So we know that in this case, 2x plus 3 is the graph on top. So if you go back to your home screen and then you do Math 9, okay, we're going to go from negative 1 to 3. If you type it in, if you type everything in, it's not right, it's not wrong, but I just want to show you that it may not feel like a big deal right now, but later on, when your functions are really messy, it's nice to be able to kind of split them up so you have to type everything on the same line. It's also easier to reference the same function without having to type everything in all over again. So if we do alpha trace, and then we'll pick y2 because y2 is the function on top, alpha trace, minus, and then do alpha trace again, y1, the x. So now that's doing it for us. We don't even need parentheses because the y1 is holding all of your bottom function, and it should 10.667. If you do math fraction, it'll convert that to a fraction, 32 over 3. I'm sorry?
Are these steps listed in the packet?
No, not really, but I can put some of the steps on the board as well. Yeah, it's similar to what we've done though, in on the previous unit, right? So just kind of getting some of that practice in. Let me go to the next page here. Now, we're not going to be able to graph these. The 1/2 y squared minus 3 and the y plus 1, not in the current form. However, we can enter this in the calculator. Okay, but if we want to do this in the calculator, guess what we have to use? Guess what variable we have to use in our calculator? X, yeah. The calculator cannot handle y. Well, if you force a y into the calculator, you can, but it's not gonna produce the answer that you want. So if you want the calculator to do this work for you, just make sure you replace everything with x instead. So just let's practice that. I think in this case, we can enter all this into our line here. So do math 9. And then we'll go from -2 to 4, and we'll just practice replacing every variable that we see with x and not y. So we'll do x plus 1 minus, now we do need a set of parentheses here. 1/2, if you want to get to that 1/2, if you do alpha y equals, will give you that math print that makes it easier to type in. Make sure you close the parentheses there. And then dx. Okay, let's try one more. And let's do this by hand first. So this is on page 3, number 2. So we have y squared plus 2x plus 1 and 2x plus 5. Which one is the graph on top? Yeah, so 2x plus 5, right? So we know that's the top graph, but let's find the intersection. I know you can see the intersection on the graph here, but for practice purposes, let's set them equal to each other and find the intersection. And the intersection will also be the bounds that we need for our definite integral. Okay, let's bring everything over to one side. Factor. Okay, so the function on top is the 2x plus 5, right? Minus parentheses. Okay, this is all power rule problem, but let's just practicing our calculator here. We can do math 9 from -2 to 2. Make sure you have your parentheses in place. Okay, same answer, right? Pretty much the same problem. All right, sorry, one last one here. Page 4, number 5. Okay. If I want to find the area of these two shaded regions here, how many integral do I need? 2. Yeah. So I think the boundaries we can easily tell by looking at the graph, right? So how would you set up your first integral for that shaded region on the left? Integral from where to where? Yep, okay, what's the graph on top? Y1, right? So I can say 3x cubed minus 3x. That's the top graph. What's the one on the bottom? 0, y equals 0, right? So minus 0 dx plus, so after I find that region, I'm going to move to the second region, depth integral from where to where? 0 to 1. Okay. Now, the second region here, what's the graph on top? 2, which is 0, right? So 0, what do you do after that? Yeah, minus parentheses, right? Minus parentheses, and then you can just say 3x cubed minus 3x. We just enter that in our calculator, and whatever that gets us, that it's going to add the two areas together. Even though one region is below the x-axis, the fact that we're doing 0 minus the bottom function will ensure that this will give us a positive number, and then it will add the two positive regions together and give us the area of those two regions added together. All right, so your homework is in your the second homework sheet or homework packet that you picked up from 7.1, numbers 1, 3, and 5, 17 to 21 odd. I'll send you guys a link to my page where the Calc chat will, you can reference those, check your answers there, as well as some of the problems that I worked out by hand on my own. All right, go get your phones.